Hi, this is Miss Wong, and we're taking notes for Unit 1, Systems and Scale, Zooming into Air. Let's remember that in this unit, we are trying to explain what's happening when ethanol burns, and we want to explain what happens to atoms and molecules in chemical reactions, that's Learning Target 1, and explain what happens to energy in chemical reactions, that's Learning Target 2. So to start out, we want to use lined note paper or a notebook to take notes for this class. So if you don't have those materials in front of you, pause the PowerPoint right now and get them. And once you've got your materials, put the title, Zooming into Air Notes, on the top of the page as well as the date. Okay, so this slideshow is going to be a review of the basics of atoms and molecules and also talking about scale and how important scale is when we're trying to explain biological phenomenon like ethanol burning. If we take a look at this jar, if I was going to ask you this question, is it empty or is it full? We kind of want to get to the question, does air have mass? If we're looking at it on the macroscopic scale right now, you might say, yeah, the jar looks empty, but in fact, air has mass, so you could also say that the jar is full. If you haven't remembered from previous classes, here's a definition of mass, which you can take down in your notes. Mass is a measure of how much matter is in a substance, and anything that is made of atoms has mass. We can test this out with air by a simple experiment where you put two blown up balloons on a stick and hang it directly in the middle on a string so that they're balancing each other. And if these balloons are identical and the amount of air in them is identical, then that stick is going to hang perfectly horizontal. So if we were going to take the air out of one of those balloons, what would that balance then look like? Would it look like this, with the deflated balloon heavier than the inflated balloon? Or would it look like this, with the inflated balloon heavier than the deflated balloon? Well, you'd find out that it looks like the second one because in fact air does have mass, meaning the air has atoms. Okay, let's consider how descriptions of air and explanations of air change when we go to different scales. So in your notes, you can write down zoom into air and then underneath large scale, macroscopic, microscopic, and atomic molecular. And next to those benchmark scales, we'll do just a real brief description of air at each of these scales. When you look at air at the large scale, you might describe it as being clear, as having clouds, or maybe other particulate matter in there. You might also describe that air or the sky has a particular color. But that's about it for large scale. So in order to make our explanation a little bit richer about air, we have to zoom in. If we zoom into the macroscopic scale, up close and personal to a cloud, we can see that that cloud contains air, but it also contains water droplets. And we can zoom into a water droplet at the microscopic scale. So now you can explain that air not only is clear and contains clouds, but those clouds contain water droplets at the microscopic scale. To make our explanation even richer, we can zoom in further to the edge of a water droplet and finally to the atomic molecular scale, where you can see that at the edge of that water droplet, you can see what was considered clear air, but now we can see that there are air molecules in the air, as well as a whole bunch of water molecules inside the water droplet. So this is at the atomic molecular scale. So all of a sudden, our description is now rich with a lot of different types of atoms and molecules that we can find in air. If we zoom in even further to that water molecule, that water droplet, then we can see that the water droplet is made entirely of many, many, many single water molecules. So now, most of our explanations in biology are going to involve us explaining what is happening to different systems at the atomic molecular scale. So let's stick with the atomic molecular scale for a little bit. First, let's write down the different kinds of molecules that we can find in air: oxygen or O2, water or H2O, carbon dioxide or CO2, and nitrogen or N2. If you want to take a look at the distribution of these gases in the atmosphere, you can see that nitrogen gas makes up the majority of our atmosphere, followed by oxygen, followed by argon, and a little bit of carbon dioxide and water. So hold on a minute, because we're saying nitrogen and oxygen and argon, those all sound like atoms, right? But we're not talking about atoms in this case. When we say what makes up our atmosphere's air, we're talking about nitrogen molecules, oxygen molecules. So now we have to consider the question, what's the difference between an atom and a molecule? In your notes, go ahead and make a T-chart, and on one side of the T-chart put atom, on the other side of the T-chart put molecule. And then pause the slideshow for just a minute and list the things on this visual that you think are atoms under the atom side and things that you think are molecules under the molecule side. After you're done listing those things, then go ahead and unpause and go on. So what you should have written down on the atom side of the T-chart are oxygen number 1, argon number 3, hydrogen number 6, carbon number 7, and nitrogen number 8, which means that carbon dioxide, nitrogen number 4, oxygen number 5, and water number 9 are all considered molecules. So what's the difference between those two things? You can continue these notes in the rest of your T-chart underneath that list. What's the difference between an atom and a molecule? So atoms are single particles that make up all matter in the universe. They're made of protons, neutrons, and electrons. So the important part here to put in your notes is that atoms are single particles that make up all matter in the universe. And you may have seen atoms represented like this, with electrons orbiting around a nucleus that has protons and neutrons in it. In biology, we're just usually going to represent atoms like plain old balls. No protons, neutrons, and electrons, just particles. And you're also going to see atoms like this, where they're part of a larger molecule. So these little plastic or wooden balls that we're going to be using for molecule models, those single balls are atoms. Molecules, on the other side, are substances that are two or more atoms bonded together. So you can see molecules represented in a lot of different ways. This is a space-filling model where the different colors of balls represent different types of atoms. There's a glucose molecule on the left and a water molecule on the right. You can see that the water molecule has two small white balls that represent hydrogen and one red ball that represents oxygen. Sometimes molecules are represented like this, where the definition says molecules are substances that are two or more atoms bonded together, and those bars that are in between the balls represent the bonds that are holding the atoms together. And this molecule is moving just to represent the fact that inside molecules, atoms are always moving in relation to each other. So this whole thing all together is considered a molecule, but it is made of atoms that are bonded together. You might also see molecules that look like this, where each individual letter represents an atom. So for example, the O represents oxygen, the P represents phosphorus, and then the bonds that hold them together are those lines that connect them. So molecules can be very small, made of just a few atoms or a couple of atoms, or molecules can be very large, made up of hundreds or thousands of atoms bonded together. The other thing to keep in mind is that most things are made of molecules, and then those molecules in turn are made of atoms. And some of you may have heard about elements on the periodic table. Elements are substances made of a single type of atom. So a substance like a rope we say is made of molecules, and those molecules are made of atoms that are bonded together. A substance like carbon, that diamond, is made up of all carbon atoms and no other type of atom. This substance sodium would be made of all sodium atoms and no other type of atom. So those are considered elements. Okay, so let's take a look at atoms and molecules in the air. We say that air contains oxygen molecules, but when we say that, we know that an oxygen molecule is made out of 2 oxygen atoms. Likewise, we say air contains nitrogen molecules, but we know that nitrogen molecules are made of 2 nitrogen atoms. We know that air contains water molecules, but again, water molecules are made of 2 hydrogen and 1 oxygen atom. And finally, we know that carbon dioxide molecules are in air, but carbon dioxide is made of 1 carbon and 2 oxygen atoms. Notice that when we're talking about atoms and molecules in air, we do not say that air contains carbon, because that would imply that air contains the element or the substance carbon. Instead, we say air contains carbon dioxide, and we know when we say carbon dioxide that carbon dioxide contains carbon, 1 carbon and 2 oxygen atoms. Okay, moving past the T-chart, we want to take down notes on 3 facts about atoms. So these are going to be important to remember. So write these 3 facts down, and we're going to apply these 3 facts to try and help our explanation for what's happening when ethanol burns. The 3 facts are that atoms last forever except in nuclear changes. That means that those particles, those atoms, are going to be around forever unless they're involved in some sort of nuclear reaction, which is highly, highly, highly unlikely. So you can just imagine that atoms last forever. Atoms make up the mass of all materials. That's fact number 2. And fact number 3, atoms are bonded to other atoms in molecules. So let's apply the 3 facts of atoms to air. If we take the first fact, atoms last forever, you want to consider these 2 questions. If this fact is true, will the carbon atoms that exist today in CO2 still be carbon atoms in a million years? And second question, will the CO2 molecules that exist today still be CO2 molecules in a million years? Write down the answers to these questions in your notes and be ready to discuss with your group why you think this way based on what we know about atoms and molecules. Second fact, atoms make up the mass of all materials. So we've already answered this question before. Does air have mass? Yes, it does. Therefore, it must be made of atoms. And then finally, atoms are bonded to other atoms in molecules. So we want to recall at this point in time what are some important atoms in air, what are some important molecules in air. And you can look back in your notes right now and just make sure that you can find in your notes what are some important atoms in air and what are some important molecules in air. If you need to, write down your answer to these questions here too so that you have 2 places to reference it, and be ready to discuss these with your group, and you can also go back to previous slides if you need to review. Okay, so now that we've been through the entire PowerPoint, here are the questions that you want to be ready for in class discussion. So first of all, people are made of atoms. We have mass. So what can the 3 facts of atoms tell us about the atoms that we are made of? So for example, if the first fact about atoms is that atoms last forever, what on earth is going to happen to the atoms in us as we grow or as we change or after we die? Ethanol is made of atoms. What can the 3 facts about atoms tell us about the atoms in ethanol? So for example, if the second fact about atoms is that atoms make up the mass of all materials, if ethanol loses mass, or if ethanol gains mass, what's that telling us about the atoms in ethanol? Finally, flames contain atoms. So what can the 3 facts about atoms tell us about atoms that are moving through flames? So if the last fact about atoms is that atoms are bonded together to other atoms in molecules, what does that tell us about atoms that could be moving through flames? So you want to jot down notes or ideas about these questions so that you can be ready to discuss thoughts or questions that you have about atoms and molecules in class. And of course, go back and listen to the slideshow again if you missed some of the notes or if you want to review some of the concepts. Thanks!